Yeah, so my name is Rathi, and I'm going to be discussing work on explaining patterns of fusion and morphological paradigms using memory-surprisal tradeoff. This is joint work with Michael Hahn and Richard Futrell. So broadly, I'm going to be discussing inflectional morphology. And so I want to start out by kind of discussing what that really means. And so formally, we can define inflectional morphology as the idea of packaging grammatical information on the abstract level into strings of phonemes on the surface level. So basically, if I have on the left-hand side here is a set of abstract features. So this is an example from Latin. What I want to do is take all these features, so the root, and then all of these like past tense, imperfective, all of that, and then map those to surface realizations. And so this mapping is what appears in Latin. So you have the root goes into its own word, the past and the imperfective kind of go together into one suffix, the passive goes into its own suffix, and so on. And so this is kind of an example of this mapping, right? And you have some 2-to-1 examples, some 1-to-1 examples, and it can differ by language and by what exact features you're looking at. But the thing to note here is that these packages of features have to be ordered with respect to one another, right? So in the Latin example, the order is ama, ba, mu, ar. But why is that the order, right? What determines that ordering? Why isn't it like ama, ar, mu, ba, right? And I want to take a step back and kind of explain by ordering. By ordering, I kind of mean a more general concept than agglutinative morpheme order. And particularly in this talk, I want to talk about the idea of fusion. And that means fusion of multiple features, as well as kind of more specific phenomena like polyexponence and suppletion, as well as, again, agglutinative morpheme order. However, I'm not going to be focusing on agglutinative morpheme order in this talk because a lot of previous work has already looked at that. So yeah. So as the title of the work suggests, I'm going to be using the tool of the memory-surprisal tradeoff to explain kind of all these phenomena. So I'm going to start by introducing what that means, and then I'm going to be going to some model simulations, and then finally ending with real evidence from real languages. So yeah, the memory-surprisal tradeoff is a theory kind of grounded in theories of language processing. And so specifically, this is about online language processing, where you have a listener who has to process words or morphemes conditional on kind of all of the previous words or morphemes in that sentence or word. And so memory-surprisal tradeoff is specifically grounded in the idea of lossy context surprisal, which essentially says that the difficulty of processing a word, WT, is going to be proportional to its surprisal, which is related to essentially its probability in context. So if a word or a morpheme is more likely in context, it's going to be easier to process. And if it's less likely, then it's going to be harder to process, essentially. But in lossy context surprisal, this is slightly revised. So you see that the conditional term in this probability distribution is MT. And what that means is it's the memory representation of context. So the idea is that our memory is imperfect. We don't particularly remember every single word or morpheme that we've just heard exactly as it is. We have kind of a lossy representation of this memory. And that leads to a worse interpretation of the probability distribution. And so we're going to increase surprisal because we don't have a perfect representation of context. But if we devote more resources, cognitive resources into memory, then we can actually improve our representation of the context and therefore lower our surprisal. But as you might notice, this comes at the cost then of adding more resources into memory. So you have this kind of trade-off between memory and surprisal, which gives us the name. And this is unique for every language. So any given language can be described in terms of this kind of trade-off between its memory and its surprisal. So to achieve a more accurate prediction of kind of future material and therefore to lower your processing difficulty or your surprisal, you have to invest more resources and energy into memory. So there's a trade-off between maintaining memory representations, so this kind of like backwards looking view, as well as predicting future material, so this kind of forwards looking view. And this can be visualized using the idea of the memory-surprisal curve, and all of this work is from Hahn et al. 2021, by the way, which the idea is that for a given level of memory, you can show the lowest possible average surprisal. And a steeper curve is going to be more efficient. And by steepness, I essentially mean that you have a lower processing difficulty associated with less information stored in memory. So you can achieve any given level of difficulty with less memory resources required. And so this is an example of two possible languages that are kind of graphed on this curve, where the memory is on the x-axis, the surprisal is on the y-axis. And you can see that the red language, which is explained by the red line, is more efficient than the blue language, because at any given level of memory, you can achieve a lower surprisal. And so therefore, we would say that the red language is kind of more optimized for cognitive resources and language processing. And each of these curves is associated with a specific order of units. So an order of morphemes, order of words, or just any other kind of meaningful units of language. And the kind of conclusion of the memory-surprisal curve is that we have this thing called the efficient trade-off hypothesis, which essentially says that the order of units in language are going to form a steeper trade-off curve. So we're trying to get to the steepest trade-off curve possible. And so languages are evolving over time. Their word order is shifting, their morpheme order is shifting in order to kind of optimize for like the efficiency of this curve. And to kind of tie this back into morpheme order, the memory-surprisal curve and the efficient trade-off hypothesis kind of result in this conclusion called information locality, which basically says that if the memory representation is imperfect, as we assumed with lossy context surprisal, we're going to minimize processing difficulty when words that, or morphemes that predict one another are close together in linear order. So kind of related morphemes, related words are going to be closer together in linear order than unrelated ones. And we quantify this prediction of one another using mutual information, which is quantity shown here. But it essentially means that higher mutual information I between two units is going to lead to more closeness in linear order. And so finally, to kind of explain how this all ties back to inflectional morphology, the primary hypothesis for this talk is that morphological phenomena can be explained as a result of optimization for the efficient trade-off hypothesis and therefore for information locality. So the existence of phenomena and cross-linguistic patterns comes out of a need for efficient use of cognitive resources and leads to kind of a more efficient trade-off curve. And so, as I mentioned previously, previous work has actually shown that the ETH can explain agglutinative morpheme order. So we're not going to be focusing on that here. What we want to look at is what else it can explain. And specifically, I'm going to be focusing on morphological fusion. So I'm going to start with some model simulations of polyexponents. So polyexponents is kind of the most basic type of fusion. Essentially, it says that you have multiple features which are fused into one morpheme. So you have this example in Latin, is, which is the dative plural. And that's two features encoded into one morpheme in a way that cannot be decomposed further. You can't split that morpheme up anymore. And so you have a 2-to-1 mapping. So that's polyexponent. And the hypothesis for this model simulation is that there is a pressure for fusion between features with high MI. So essentially, when you have features that are high MI and fused, it's going to lead to a more efficient trade-off. And essentially, the idea is that you have these high MI features that are so close together in linear order, they actually want to be stacked together. Instead of just next to each other, they turn into one morpheme together, they just fuse. And so to test this, we simulated a language with verbs expressing 3 different binary features. We arbitrarily assigned 4 times frequency for the second singular and third plural, which essentially introduces non-trivial mutual information, which can allow us to make actual distinctions. What this leads to is that person and number have high MI and person and tense have low MI with respect to one another. And so we can generate 2 different languages. In the high MI language, we're going to be fusing person and number. And in the low MI language, we're going to be fusing person and tense. And these are all artificial languages. So we generated trade-off curves for both simulated languages. And so you see these here. The low MI language is in red, the high MI language is in blue. And you can see that the blue language is more efficient and has a steeper trade-off curve at all levels of memory. So for any given level of memory, the high MI language is achieving a lower surprisal. So what that means is that when you have high MI features being fused, it leads to a more efficient trade-off. And the reason for that is that the fusion of features that are kind of predictive about each other is going to lower your entropy and it's going to lower your surprisal overall. Whereas if you have fusion of unrelated features, it's going to lead to less change in entropy. The next thing I want to look at is triple exponents and suppletion, which are, here I'm going to be looking at data from real languages. So triple exponents is a specific kind of polyexponents where you have three features that are all polyexponent with one another. So this is really common cross-linguistically for tense, aspect, mood, and person, number, gender. So what we would expect is if the efficient trade-off hypothesis holds, in this optimal ordering of morphemes that you can generate, which leads to kind of the most efficient trade-off curve, you would expect tense, aspect, and mood to be very close to one another, and you would expect person, number, and gender to be very close to one another. And so to kind of formalize this, we essentially looked at the standard deviation of tense, aspect, and mood, and of person, number, and gender. And if you have a lower standard deviation, then they're going to be closer together. And so you would expect that if you look at all possible triples of features, TAM and PNG are going to be the kind of on the much lower end in terms of standard deviation than in general. And we normalize this by the number of features in a given language. And then we average this over all languages, and we took all three feature combinations that had more than 7 language data points. So you can see this plotted here where the standard deviation is on the y-axis. You can see that tense, aspect, mood, and person, number, gender are actually both lower than the average standard deviation by 3 features. And this is significant by t-test. So yeah, essentially this confirms the hypothesis of the ETH. The other thing we looked at here was suppletion, which is a phenomenon where roots take more than one form when they're inflected for a feature. So an example is go in English, where in the present and the future tense, it's go, but in the past tense, it's went. And so the root word is changing to inflect for a given feature rather than a suffix or a prefix. It's actually changing the entire root. Cross-linguistically, it's been shown that number suppletion is a lot more common than case suppletion. So that means that nouns are more commonly suppleted by number rather than suppletion driven by case. So essentially, we considered suppletion to be a form of fusion with the root. So the idea is that a feature that causes suppletion is actually fusing with the root rather than just kind of being a suffix. So the ETH would suppose that suppletion driving features like number should be closer to the root in optimal ordering than others like case. So basically, we would look at optimal ordering, and then we would see does number tend to be closer to the root than case across languages. And we actually found that this is true across 17 languages. 15 of those showed this phenomenon with, again, significance by binomial test. So this again confirms the ETH, or what we would expect from the ETH. Finally, I'm going to be looking at informational fusion. So previously, we looked at fusion as this kind of binary concept. Things are either agglutinative or they are fusional, and there's no in between. But previous work has argued that fusion is actually better thought of as kind of a gradable measure, where things can be fused to a greater or lesser degree. So an example is in Latin, this bonarum, which is an adjective. It's the feminine genitive plural, where arum is the suffix. Rum corresponds to the genitive plural, and a weakly corresponds to the feminine. It's not a super strong correspondence though, so you have somewhere between agglutinative and fusional. It's kind of halfway. And this is true across languages. Kind of almost all forms actually have a gradable level of fusion. And to quantify this, we used informational fusion, which was introduced in Rathi et al. 2021. I'm not going to go into specifics of how this is calculated, but the idea is that you can use a probability distribution to actually get a level of fusion, a numerical level of fusion for any given form. So how does this relate to morpheme order, right? What we want to look at with informational fusion essentially is what features tend to be more fused, what causes features to be more informationally fused with one another. And the hypothesis is that high mutual information morphemes are going to be more fused. And so fusion corresponds to closeness in linear order. To kind of look at this, we used a measure called pairwise fusion, which again, I'm not going to go into the specifics. You can see that more in the paper. But essentially, this gives us a value of fusion for any 2 given features in a language. So we compared pairwise fusion with optimal ordering from the ETH. And if 2 features have high fusion, they should be adjacent in optimal ordering, or at least very close to one another. So to determine this optimal ordering, we used data from universal dependencies. We averaged out the ranks of each feature by feature category, and then we use this kind of optimal category ordering to find the difference in rank. And then we plotted this difference in rank against pairwise fusion. For fusion, we used data from Unimorph, and then we used an LSTM sequence-to-sequence model with attention to actually find the values. Again, I turned to the paper for the specifics. And so the hypothesis is that fusion is going to trade off with difference in rank. So things that have high difference in rank are going to be less fused in general. So we used 4 languages based on variance in their verbal paradigms. So we used Arabic, Latin, Spanish, and Portuguese. And these are our results. So we can see that Spanish, Latin, Arabic, and Portuguese, all 4 languages, have this empty upper right quadrant. And so what that means is that no morphemes are both highly fused and far apart in optimal ordering, which is what we would expect in accordance with the ETH. And this is significant for all 4 languages. We did a stochastic test with a permutation test with area under the curve, and we found this upper right quadrant is empty significantly for all 4 languages. So yeah, basically we have extended the ETH as a broader model of inflectional morphology. So instead of just focusing on morpheme order in the agglutinative sense, we've kind of used it as a tool to explain morphological fusion. And we've shown that certain phenomena, fusion, and can lead to kind of more efficient trade-offs. We've also shown that category clustering and circumfixation can as well. That's more details of that are in the paper. And we provided evidence that the ETH can also predict gradable fusion, which I just talked about, as well as cross-linguistic patterns of exponents and suppletion. So in future work, we really want to look at how far this kind of trade-off can go. Can it explain phenomena like language-specific patterns, further cross-linguistic patterns, the existence of more general phenomenon, the existence of morphology in general, right? How far can it actually be used as an explanatory tool? Yeah, thank you.
Great, thank you. I think we have time for 1 or max 2 questions. I have a question, but I will cede to the floor to somebody else if they have one. No. Okay. Thanks. This is really interesting. I'm kind of confused about, so in the broader ETH, the value of adding a memory term, I think, right? Like that's kind of clear within the surprisal framework for language modeling because you're looking at long sequences. I think it's the value of the memory trade-off is maybe a little bit less obvious when you're looking at, I mean, inflectional morphology. You might expect it to have a stronger impact if you had like longer morpheme sequences, right? But it seems like the pressures are a bit different. And there has been other work, looking at just inflectional morphological paradigms in terms of surprisal. So I'm wondering if you did any kind of baseline comparisons, right? With just like how much does the ETH get you, in additional explanatory value versus, for example, like pure surprisal estimation of, within paradigms, because the value it adds in this context is not entirely obvious to me.
Yeah, I think, so yeah, with word order, it does, I think, seem more intuitive, and previous work has also used the ETH to explain word order, and it's been successful in doing that. I think we didn't do any baseline comparisons. I think that would maybe be useful to look at. But yeah, I don't know. I think the value of memory is still relevant in some contexts, especially when you have much longer strings of morphemes. But yeah, in examples like Latin, you only do have a few morphemes, so it is something to look at. Yeah.
Yeah, because my sense is also that it's an intuitive finding that morphemes that appear often together will tend to fuse, but it's like that can be captured by just looking at mutual information between them, right? So I think comparison to some more naive baselines would maybe make the value of this particular hypothesis a little bit more clear.
Right. Yeah.
Cool. Does anyone else have a question? Nope. Then let's thank the speaker again.